our next presenter is going to be Avi Telyas. He is from Mellanox, the Director of System Engineering, and he is going to be giving a presentation about building the most efficient machine learning systems.
I may repeat some things that we mentioned today because we are all talking about the same field and same systems. Just a quick introduction of myself. My name is Avi. I manage the technical team in APAC, so from India to Australia, and I live in Tokyo actually. I think that I started to see AI system, machine learning system in Japan maybe 4 or 5 years ago. You can say that maybe Tsubame 2 was HPC system, not a real AI system, but now when you see a Tsubame 3 and when you see AIST, you see that it's shifting to AI. I will skip some generic marketing slides. I think we all know what's going on in the world. I just want to mention to you a bit what we see and how maybe HPC is connected to machine learning. There are some things that are shared, there are some things that are not so shared. And I will talk a bit about technologies that we use for HPC and also for machine learning. Again, okay. I will talk about this slide for a few seconds. So, if you know Mellanox, you know that we provide end-to-end networking, which means we don't provide only the switch, we provide the HCA or NIC card, we provide the switching technology, and also the cabling. Okay? I will talk mostly about InfiniBand today, but as we see, there are also machine learning systems with Ethernet. And I think that we have the appropriate Ethernet systems also for that. For example, the DGX2, I think I have a slide on the DGX2, can support InfiniBand and Ethernet. So the customer has a choice. I still think that InfiniBand has better tools for machine learning, which I'll talk about it later, but you can still deploy it with Ethernet. There are some other things that we are doing that are less relevant for machine learning, but it is relevant for cloud computing. It is relevant to building systems. And we're talking about smart NIC, NVMe over fabric. It's about the entire infrastructure. I will not talk too much about it, but if you have questions, please ask me or during the presentation or even afterwards. Again, I'm skipping the marketing slides. Sorry about that. Okay. So it's only the partial ecosystems of what we have. I put in Chainer. I removed Paddle and I put in Chainer because I think Chainer is very popular in Japan and for a good reason. And we see many deployments here in Japan with Chainer, but again, the end user has a choice. If you go to university and ask students what do you use, you will probably get 4 or 5 different answers. Why? Because each person, some of them like Torch and PyTorch, some of them like Caffe, TensorFlow, and many in Japan like Chainer. If you go to Singapore, you will hear almost nothing about Chainer. But again, that's the way it is. Some of the big companies that are doing machine learning research that are very active in this field. I think we talked a lot about Sierra and Summit. I have maybe 1 or 2 slides later about them. As mentioned earlier, we are right now at the finishing stages before the ISC. I think it was a very interesting project. It includes integration, again, of the Volta, of Power9, of Mellanox. I don't know if we talked about PCI Express Gen 4. So Power9 supports PCI Express Gen 4 to our HCA. And that is also, I think, probably the first CPU in the world to support it. I know that other CPUs may support it later, but I think it was very important for this project to get the bandwidth that we wanted to get. This is also in deployment right now, the ABCI system. That's with Fujitsu, not with VM, and that's not with Power, but still it's with the voters. And I don't think the rest is really important. Oops, that's not what I want to do. Okay. I don't want to talk too much about the DGX2, but if you look at the way most clusters like ABCI and NVIDIA build the system, there is some kind of a ratio between the numbers of the accelerators that you have and the bandwidth that you want to push out. So specifically for the DGX2, there are 8 Mellanox ConnectX-5 at the back. So there are 16, right? 16 volts, and there are 8 at the back. With the DGX1, there was a ratio of 8 to 4. So the ratio is again, that's the ratio. Why? I think it's a matter of, let's say, cost performance. NVLink is strong, and NVLink, I think, is used to have communication within the server. But once you want to go out, I think this is the ratio that currently is being used. I think we've talked about this enough, and the internal architecture. I think once we announce at IC, we can show more about the design of the system. So the network is a combination of large director switches. We have 648 port switches, which form the backbone of the system. It's a full bisection system. And of course, we have one new system that are top of the rack that connect to the local system. I also mentioned here, yeah, so it's a ConnectX-5 EDR system. So in the InfiniBand, current technology is EDR, which means 100 gigabit per second per port. ConnectX-4 was launched, I think, 2 or 3 years ago, and ConnectX-5 was launched, I think, last year. And it does support 100 gig as well as EDR, but what ConnectX-5 supports, it can support PCI Express Gen 4 by 16, which means that from a single HCA, you can actually drive 200 gigabit per second from both of the ports. And that's very important for this system. These are some of the technologies that we have. It's not only a pipe, okay? So if you think about Ethernet 100 gig, the network is a pipe. You have routing algorithm on a network, you decide how to move it around, but it's just a pipe. It doesn't do anything besides moving data. When we talk about InfiniBand, and we talk about our technology, we always add technology in the HCA, in the switch, to improve performance, to provide more offload on some of the compute and some of the transport to be able to do more. And I will talk on some of these technologies. Something that I will talk about is GPU Direct, that it's mostly a pipe, but it allows the communication between GPUs to run faster. I will talk about sharp technology. It's a capability in the switch to do aggregation, to do some kind of computation in the switch, instead of do it in the CPU. And that improves machine learning and also some HPC application. NVMe over Fabric is a new technology. I think, again, the Sierra and Summit using NVMe as PCI Express card. They use flash storage on each server. But why use it only on the server? Why not put it in the network and access it remotely in almost the same latency as local storage? And this is, again, a recent technology that utilizes RDMA, mostly on Ethernet, but also on InfiniBand, to access storage. And I will mention some more technologies that we have. So again, it's maybe repeating what I said before, is if you think what the CPU is doing, and if you think about maybe some Ethernet technologies that are not RDMA, the CPU is doing the network. The CPU is doing all the computation, and the switch is just a pipe, the network is just a pipe to move data. And right now what we're trying to do is we're trying to improve the network, and that will improve the overall communication. And I will try to explain it a bit because it doesn't make sense. Okay. I think I have some slides later, and if not, I will talk about it. These are just some of the numbers that we see in the improvement that we see when we utilize technologies. So we see some improvement in computation, 10 times. I think maybe it's a marking fact that's over exaggerates the results, but we do see real improvement in collectives computation when we run a sharp algorithm. The shield, once you build large network, what happens if you fail? What happens if a cable fails? How do you handle it? So the technologies that we added called shield actually help us fail over faster. So the MPI drop of whatever you're running on it doesn't break. Okay, this is very important. Okay. So just a few words on what is RDMA and what are the main differences between non-RDMA communication. So I think everybody knows the standard model of actually application, some kind of socket, library, moving data to the NIC and then transferring and then all the way back. Okay, so it goes, usually there are at least 2 buffer copies somewhere in here. Okay, and that's not really efficient. Also, if you look what happened in some security exploits that were published recently, is that once you force the kernel to do more, then you slow down your network. And what RDMA is doing, RDMA is basically some kind of a, I don't know how you call it, a fast pipe or a kernel bypass technology from the application directly to the RNIC, the RDMA NIC or HCA, whatever you call it, and then move directly to the buffer on the destination. And this is actually, you can see that we don't go through the kernel. We don't do buffer copies that are not necessary. We are not affected if, for example, there is a spectral meltdown, a security patch that slows the kernel. We are not affected by it because we don't go through that. Okay? And that improves latency. That also, again, improves, you don't switch, you don't waste your time going to the kernel and back. And this is something that improves. And the slides talk about RoCE, so RDMA over Ethernet, but again, it's the same technology in InfiniBand and Ethernet. InfiniBand is slightly more effective, mostly in the switching, but also slightly in the packet of the InfiniBand over the Ethernet. But basically, it's the same technology that underlies underneath it. So it was mostly used for HPC, but currently, even if you go to Microsoft Azure, you will be able to see RDMA communication in the storage and some non-storage application that they have. So what is a GPU direct? Oops, I don't know why I clicked. So I think we introduced, there are several generations of GPU direct, generation 1, generation 2. Some of them were between GPUs, and then I think at some point there was a need to actually communicate in the network, and this is something that we did with NVIDIA. We need to copy data, and we need to copy data from one machine to another. Okay. NVLink is handling the communication within a server between GPUs, and what happens when you go to the network? what happens when you scale. And this is where GPU direct comes. And again, it's an RDMA communication. So we can copy data from GPU memory on one server and move it to another server without doing anything on the CPU. Again, if you do normal networking, what you will do usually is you take the GPU memory, copy it to the CPU memory, then build a packet, copy it once or twice, and then move it up. This is what you usually do. With GPU Direct, we don't do it. We just copy data from one GPU memory to another location in the network. Of course, there is integration with CUDA. You need to know what you're doing. But again, that improves overall latency. And that will improve overall performance because you spend less time moving data. Some numbers, latency and bandwidth that we see. We don't see actual application performance because applications sometimes are difficult to show exactly why the GPU target improve the performance, but this is something that we experience in many places. Yes, I don't know, but okay. So I think the slides are. I was thinking maybe this should be after the explanation of the shop, but I will start with the performance, and then I will talk what it is. So this is InfiniBand again. RDMA can do both Ethernet and InfiniBand, but this is our EDR technology shop algorithm. We added the capabilities in the technology is called Switch IB2, the silicon Switch IB2 technology. It's in EDR to handle collective, to handle some aggregation. So it's all reduced. It's reduced, right? But it's and barrier. So basically, you can do some of the computation or some of the collectives in the network. Okay, and this is the performance number that we see. Just to show you, this is shot in 8-byte line, 28-byte, and the comparison between our network communication and software-based communication. So you can see that hardware-based shop, hardware-based collective is quite flat. There is some kind of bump here that I will explain later, but still it's much lower than software-based collective. Shop cannot handle everything, of course. It's limited in what it can do. But what I will talk about later is connection to machine learning, connected to AI, and our next generation. So this is with Switch IB2 and EDR. We already announced HDR. HDR is 200 gigabit per second. That will be available later this year and has improvement of sharp technology, especially for machine learning application. I will mention it later. So usually when you run a machine learning application, you need to share data. You need to hold the parameters somewhere. So there was a model that say there's a parameter server that all the different, when you train, okay, that you do calculation and then you push everything to the parameter server. It does something with it and then spreads the result to everybody else. That was one model, and that obviously you can think that the parameter server becomes the bottleneck in computation. And another model is to try to do it in parallel, okay, to let the switch do the simple calculation and then spread the data to everybody. And this is what we're trying to do with machine learning. So again, oops, I think I want to slide this. Okay, so I will talk about it without good slides. So what basically Sharp is doing? Usually you have a full bisection tree of compute, right? And then you want to do, let's say, a barrier. A barrier is a collective that says only when all the compute nodes reach the same place in code or the agreed place in the code, only then continue to the next step in calculation. So usually what you do when you do a barrier, you do a lot of communication between the compute nodes to say, okay, I'm done, I'm done, I'm done, I'm done. And then you spend a lot of time doing this communication, and when everybody is done and passed the barrier, then you continue. What we do with SHARP is that the switches themselves can do this. So each compute node only sends data to the closest switch, that's it. And the switches themselves build a tree of computation, of aggregation, and then one switch at the end, at the top, says, okay, it's done, and then multicast to everybody, it's done, continue. So if I go back to the performance number, and you see this bump, this is exactly when we go over a switch, okay? So if you're on one switch, that's simple, one switch will do it. When you have a two-level switch, then you have a two-level communication, and that's it. But if you think about the number of messages that you actually send, the compute sends is one stating the status, and then one to get the result. That's it. The compute only sends two. One send, one receive, and that's it. The switches themselves do the calculation. Okay? When we compare to standard computation, then actually you have many more, log something more. So I reached OpenPOWER, and we talked about it. We are one of the founders. We are doing a lot of integration. We started with Power 8 and now with Power 9. There is copy related, open copy related integration that we're doing. And this is a slide that I've seen earlier. I think this is the Avi slide. This is a bit old. I think right now Nickel 2 is the one that is being used when you go into the network. And that is work that was done by NVIDIA with a lot of discussion with Mellanox is how to do the integration correct. And this is something also that we plan to improve in the future when we move into HDR and again the SHARP 2 algorithm. Then we plan to improve the communication libraries that will help us scale better. But all of them, yes, have integration to RDMA communication. So chainer MN, the scalable chainer is using Nickel 2, mostly Nickel 2, and it relies on MPI for communication establishment. TensorFlow has RDMA libraries as well as Café, etc. So all of this library actually rely on offload communication to improve the overall computation. I think I'm done too early, but that's okay.
Okay, let's give a round of applause to Avi. Thanks, Avi, for the presentation.
Thank you.